This module we're going to talk about caching, and that's about what we put in cache is items that we're going to be accessing often or likely to be accessing soon, because the cache is going to be made up of the most expensive and best performing memory. So we want to make good choices about what goes in there. So we want to make sure, the things that we're most likely to have to access are in that cache where the performance is best. And we figure out what might be likely to be accessed by thinking about locality of reference. So if we have accessed a particular address, it's likely we may access something near that address again soon. In repetitive loops, items in arrays and structures might be put together. So one bit of locality we're going to talk about is spatial locality, and we're going to show how the cache takes advantage of that, or the choice of what goes into a cache is going to take advantage of that. We're also going to talk about temporal locality. So we talked about in space, instructions are accessed sequentially most often. I mean, only when there's not a branch or a reference call. We're going to just get the next instruction in memory. So we might as well, that's a definite locality of space. And temporal locality, we're saying if we've used an item from memory, a data item, once, maybe we'll use it again. So if we've used it, we're going to keep it handy. And that's another thing we do with the cache, is keep stuff handy that we've used recently. And that's temporal locality that we're taking advantage of. And we've seen this. This is the different kinds of memory and how the most expensive memory is on top, but it has the best performance. And then things like removable hard drives that are cheapest but have the worst performance would be the bottom. So the thing we're going to put at the top is the registers, because that's items in registers are most likely to be accessed. And then we're going to learn this week about caches, and that is going to be using high performance memory. Then main memory, which is where if we've loaded a program, it's in main memory. And then data we're saving is in the rest of this. It's like we just talked about, the registers, the data we're going to use for operands is in registers. And then we're going to talk this week about caches that are constructed with somewhat high performance memory. And we're going to talk about multiple cache levels this week. And again, the level 1 cache that we'll understand shortly is usually on the chip with the CPU, and the registers would be in here. The level 2 cache is closest, and then there's the main memory. Okay, so how does cache memory work? We want an item. If it's not in a register, we're going to bring it in from main memory and say we want a word. So say in MIPS a word is 32 bits. We're not just going to go to main memory and get the 32 bits and put it in the cache. We're going to bring in a block, and a block is going to be a lot bigger than 32 bits. We're going to bring that whole thing into cache. And the idea of that is, one, we don't want to spend a lot of time on just bring in 32 bits. We want to make the time more worth it and bring in a whole block. And if we need something in one particular address, we might want something close to it later. So if we bring in a whole block, it'll already be there. And so blocks generally are going to take hundreds of bytes, even though what we want is 4 bytes. We're going to bring in a block that's much bigger, and we're going to copy it from main memory into the L2 cache. And then what's in L1 is going to be a subset of what's in L2, and we'll see how that works. So here's some definitions. So when we want a item from memory. So again, remember, the only time we're going to access memory is with a load word or store word. Let's say we get an address that we want from memory. When we find that data in the cache, that's called a hit. So if we say, I want data at a certain address, and we look in the cache and it's there, that's called a hit. If we look in the cache and it's not there, that's called a miss. The hit rate is the percent of references found at a given memory level, and hit ratio is just the ratio. So the hit rate would be between 0 and 100, and the hit ratio would be 0 and 1. And obviously multiply the hit ratio by 100 and you get the hit rate. And the miss rate is 100 minus hit rate. The hit time is the time needed to access data at a given memory level. So there's going to be a certain amount of time. If something is in L1, that's going to take a certain amount of time to get out of L1. A miss penalty is the time required to produce a miss. So it might say, all right, if I have to look in L1 and it's not there, that's going to take time. Then I have to look in L2. And either it's there or it's not, and if it is, I have to spend time getting it. So the miss penalty is going to be the time I spent looking in L1 and not finding it, plus the time it took to find it in L2 and bring it back. So that's the miss penalty. And the effective access time would be averaging out how the average amount of time each reference is going to take. So if you're going to average, if you say the hit ratio is 42%, we're going to use that information plus the hit time and the time it takes to do a miss, which would be 58%, and calculate an effective access time or average access time. And another thing is called a line. So in main memory we have a block. So when we get data out of main memory, we're going to take a block. And then when we put it in the cache, it's going to be called a line. And it's just annoying because the size of a block and the size of a line are the same. It's just in the main memory it's called a block, in the cache it's called a line. Just an annoying thing you have to get used to. So now we're going to look at how long it takes to process data when we're trying to get it from memory. And there's two methods of doing this. There's look aside and look through. We're going to look aside first. So this is saying, all right, there's a certain amount of time that it takes me to get data out of the cache. And then this memory is the amount of time it takes me to get data out of main memory. Okay, so getting data out of main memory takes longer than getting it out of the cache. In look aside, what it's saying is I'm going to start my look in the cache at the same time I'm going to look in main memory. If I find it in the cache, I stop this. If I don't find it in the cache, I keep going. So if there's a hit, this is the amount of time it takes, is TC. If it's a miss, this is the amount of time it takes. It requires two traffic over two different buses at the same time, but it lowers the effective access time. This is your only miss penalty, is this. So here's an example. Main memory access, so that's TM, is 200 nanoseconds. Cache access time, TC, is 10 nanoseconds. So that's why we want stuff we know we're going to access to be in here. It's considerably better. And we have a hit ratio. That's a hit rate. You have a hit rate of 99%. And so we're doing look aside, which means the access occurs concurrently. So the average access time, or effective access time, would be 99% of the time it takes 10 nanoseconds, and 1% of the time it takes 200 nanoseconds. So this is the average access time is 11 nanoseconds. Look-through caches are a different kind, and that's where first you look in the cache, and if you don't find it, you start at that time looking in memory. So if you have a miss, the time to process a miss is this plus the cache access time plus the memory access time. So here the average access time would be the hit ratio times the cache time, and then the miss ratio times this added together. Because if you have a miss, this is the time it's going to take, this whole thing. So this is your penalty, is the whole TM. So with our same example, our average access time is the 99% doing 10 nanoseconds, then the 1% is the 10 plus 200 is 12. So it's a little higher. And this is 2.10, so 9.9 plus 2.1 is 12. So caching really only works if we're accessing items that are close to each other in memory. So if we don't, and we're bringing in this giant block that we're not using, and we end up having to take this big block out and bring in a different one, it actually could make performance worse. But if we have good locality, caching is beneficial. If we don't, it's not so much. So the other thing, because caches are used for reading and writing, so if we have a store word and we're writing to a certain address, what happens if we write to an address that's in the cache? So right through, if we're writing something that's in the cache, we update the cache and the main memory at the same time. So we really don't get any advantage to having something in the cache on a write. Write back only updates the cache, so that's going to be a lot faster. But then main memory has to be updated when the item is removed from the cache, and we have to keep a recording of whether that main memory is dirty because the cache was updated. As we're going to see, a cache contains only a fixed number of lines, and it's a lot smaller than main memory. And then if we don't have a hit, and we have to go to main memory, we're going to put that new thing we had a hit on back into the cache. What if the cache is full? We have to find a way to replace some line in the cache with this new block that we've brought in. So we have to come up with a replacement policy if we're changing what's in a full cache. And random is a replacement policy. Just kind of, if the whole thing is full, just kind of pick a line at random and say, you're out of here. First in, first out, so whichever's been in there the longest gets taken out. Issue with that. It could be in there the longest, but what if it's getting used a lot? It's been in there a long time because it gets used a lot. That might not be good. And then least recently used, which makes the most sense, but is rather hard to carry out. It's complicated. And we've talked about Harvard and von Neumann architectures for main memory. What about caches? Do we have instructions and data in the same cache? That would be a Harvard cache. Or do we have an instruction cache, a data cache? And that's actually fairly common to have separate caches for instructions and data. And we can actually have an L3 cache. So hopefully in your papers you talk about the how many levels of cache there is, but you could actually have 3. And you could have 2 of them in, 2 levels in the CPU or on the same chip. And then there's a thing called an exclusive cache, which doesn't let you keep multiple copies of the data in the different levels of cache. So when we start up a computer, the cache is going to be completely empty. So that means that everything you do is going to be a miss at first until you fill up the cache. We're going to talk about different ways of putting items into a cache. If you put it in there randomly, or anything can be anywhere, you could have a capacity miss because the whole thing is full. And so what you want isn't there. Or conflict miss, we're going to look at, there's a way of organizing your cache so that the address in the cache is directly related to the address in main memory. So even if the cache isn't full, it could be that the line that corresponds to the address you're looking for happens to be full. And we'll see that soon. Okay, so finally we're going to look at mapping schemes, which is kind of what part of that previous slide gets to. So we're going to consider how we determine, once we take something out of main memory, and we're going to talk about, main memory is addressed. Once we get something out of main memory, how do we figure out where to put it in the cache? And there's 3 main ways. Fully associative and direct map are kind of complementary or different, opposite. And then set associative is kind of between. So again, we've talked about the 3 cache organizations that we're going to examine. And the idea is that there's a block number. So we have main memory. And if a block size is 256 bytes, we say block 0 begins at address 0. Block 1 begins at address 256. Block 2 begins at 512. And so on. And that you can get a block number by taking the memory address and dividing it by 256 and taking the right. So we want to know, again, we have a block size, and we want to find, if we want an item, it's going to be within a particular block. Okay, so an address is a byte. So we have an address of a byte. And it's going to be within so 1 byte is going to be within a particular 256 byte block. So we can figure out, when we get an address, what block is it in, and where is it in that block. So again, the block number, as we talked about earlier, would be, we just take the address and we divide it by the block size. And then once we have that, the block number, we can figure out, based on the lower bits, where it is in the block. So if we have 256 byte blocks, an address is the address of a byte, we divide the address by 256 to get the block number. And look at that, it's just the upper bits, right? So the upper bits describe the block number. And then log 2 of the block size is then the number of bits that describe the offset within the block. So if I'm looking for an address, if my lower bits here, well here it's E8, but say I'm looking for an address in this 256 byte block, but I'm looking for a particular byte. If those lower 8 bits are, if that's the lower 8 bits, I'm going to look for byte 3 in this block, so I'm going to say, all right, so I'm going to go to 0, 1, 2, 3. This is my item, this is my byte. So this is going to describe the offset within the block. This is where I find the block in memory, and this is going to describe for me where in that block it is. I get the block number by just taking the upper bits. I figure out how big this offset is by taking the log of the size of the block. Take the log of the size of the block. Everything above that number of bits is the block number. Everything below, everything within that is the offset. So a cache, main memory is going to have a number of blocks. A cache is going to have a lot fewer. So again, as we said earlier, in a cache it's called a line, and in the main memory it's called a block. They're the same size. So a line is going to hold one block. And how we're going to map how a block can be put in a cache, like where it can go, is that the mapping that we're going to talk about, and that's the fully associative, set associative, or direct mapped. Okay. So the number of blocks in main memory is going to be the memory size divided by block size. And of course, the number of lines in a cache is going to be the size of the cache divided by the size of a line. So we say if we have a cache size of 8 kilobits and a line size of 256 bytes, which is the same as a block size, how many lines can it hold would be 8 kilobytes divided by 256, which is 32. So this cache can hold 32 lines. That's a pretty small cache. So remember, a kilobyte is 2 to the 10th bytes. 8 is 2 to the 3, so this 8 kilobytes is 2 to the 3 times 2 to the 10 bytes. 256 is 2 to the 8th bytes. We divided 2 to the 13th, divided by 2 to the 8th, and get 2 to the 5th, which is 32. So it's kind of just going through that calculation. So again, repeating, the block is the basic unit of transfer. We're going to transfer a block. If you have a miss, we're going to take an entire block. So if we're looking for a particular byte, but if we don't see that byte, we're going to bring in an entire block, which could be a lot of bytes in. And then we're going to talk about how we organize a cache into sets. And associativity is the number of blocks per set. And so we're going to see all the extremes from where the associativity is 1 to the associativity is the entire size of the cache. So that earlier one, it was 32. And then in between, we're going to see a variable number of sets. So the first one we're going to look at is that one on the right in that earlier one, where fully associative, a set is the size of the cache. So any memory block can go to any empty cache line. There's just one set. And so every time you need to detect whether something is in the cache, you have to look at everything in the cache because anything could be anywhere. So if you want to do that in any amount of reasonable time, you're going to have to look at all the lines in parallel and be able to look at them all at one time. If a line is occupied, there's going to be a valid bit there. And if there's a miss, we look for an empty line and put it there. If there's a miss and there's no vacancies, we have to figure out how we're going to replace, what we're going to take out to do the replacement. So this is similar to before where we had that offset size. And we're going to divide the address into two fields, just like we did before. So before we talked about the block number being in these upper bits. Here it's the same thing, but we're calling it a tag. So if we have 14-bit addresses, so this 14 bits describes the address in main memory of a byte, and we have a cache that contains 16 lines, and each line is 8 bytes. So that's the same as a block, remember? So the size of a block or a line is 2 to the 3. So the offset in the block is going to be 3 bits, is going to describe that. And then the rest of the address is going to be called the tag, or the block number. So we're going to look through our 16-line cache and see if any of those lines have this tag in there. If it does, it's a hit. We're going to go in there, go to this offset in the block, and get our piece of memory. And then every line in the cache is going to have a tag, just like we said. And we're going to look at the valid bit and then look to see if the tag matches. And if there's a miss, if none of them match, we have a miss. Here's another view. So when we ask for a memory address with our load word or store word, here's going to be the whole address. The upper bits is going to be the tag, and we're going to look in all of these. These are all the lines of the cache. We're going to look in all the lines and see if the tag matches. If there's a match, we go there. And remember, this line is a lot more bytes than the 1 byte we're asking for. So we figure out where in this line the particular byte we want is by looking at the offset. The number of bits in the offset is log 2 of the line size. That's how many bits describe the offset, and the value of it tells us where in the line we need to go. So here's our traditional address size that we're going to, we deal with in MIPS is a 32-bit address. And so if we say we would like to access this address in memory, and we have a block size of 256 bytes, log 2 of 256 is 8. So the lower 8 bits is the offset within the block that we're looking for, and the rest of the bits are the tag. So the tag is going to be the upper bits, or we divide it by the block size. Or, obviously you can just take this upper part, and that's the tag. So we look at all the lines of the cache and see if this is the tag, and then we go to this offset in the block if it's a hit. So fully associative is one extreme where any tag can go in any line. Direct map is the other extreme where we actually use the part of the bits of the address to figure out which line it maps to. So if we have n lines in the cache, we calculate a block number. Remember, the block number was the tag, basically. Well, we use some of these lower bits of that tag field to calculate a line number. And the line number would be the block number modulo n, which is the number of lines in the cache. So if you had 10 lines, line 6 can hold block anything divisible, anything that has a remainder of 6 when you divide it by 10 could be, so if we're looking for address 6, it'll be in line 6. If we're looking for address 16, it'll be in line 6. 26, so anything where if you divide it by 10, the remainder is 6, that's going to be where it belongs. But let's go through a more specific example. Here's a simple example. So if we have a main memory with 8 blocks, obviously that's a tiny main memory. But if there's 8 blocks in our main memory, the block number requires 3 bits. So we're going to have block numbers between 0 and 7. And if we have a cache of 4 blocks, the lower 2 bits are going to describe what line number in the cache it goes to. So this 1, 1 would go to this block. And then this one, the lower 2 bits are 1, 1. This would also map. So we're going to see what kind of potential problems that could cause. It is actually, if you want block 6, you do 6 divided by 4. And then the remainder is 2. So 6 mod 4 is 2. That's the remainder when you divide 6 by 4. So this is going to go into block 2. So as you might already be able to see, if I know what block I want, I know where to look for it, but there's several different choices that could be. So that's where our hits and misses come from. Here is if we get to this block and it's not the right one, because here could be block 3 or block 7. So with direct mapping, we're going to split our address into 3 fields now. So we had the offset, that's still the same thing. This is the log 2 of the line size or block size. The next field is going to be the line number, and that's going to be log 2 of the number of lines. So if we have 8 lines, this is going to be 3 bits. And then the rest is this tag. Okay, so we're going to go, we get an address we want to go to. We're going to calculate the line number in the cache that it should be at. We go to that line number, look at the tag, see if the tag matches. If it does, it's a hit. If it doesn't, it's a miss. So here we have a main memory with 4 blocks. That's pretty small. But our main memory is 4 blocks, and each block is 4 bytes. So that means our offset is log 2 of 4. So that's 2 bits. Describe the offset. Our cache contains 2 lines. So log 2 of 2 equals 1. So our line field is going to be 1 bit, and what's left is 1 bit for the tag. So continuing with our simple example, if we're looking for address 3, so remember we have a 4-bit address, and we're saying, all right, we want address 3. This is the offset. This is the line number. So the line number is going to be 0, and our tag is going to be 0. So here's the block we want in main memory. In the cache, it's going to be in line 0, so that's here, and then this is our tag of 0. If we then wanted to use block 2, Block 2 would have an address that starts with 10. Remember, the block number is this outside of the offset. So if we wanted this right here, this would be address 10, and then our offset would be 10. So here, the tag would be 1, the line would be 0, and the offset would be 10. So this would be where that piece of memory would be. And if we wanted to look in the cache, we'd look here, and we'd look in line 0 and see that the tag is not 1, it's 0, so that would be a miss. So here we show it again. If we wanted address 1010, we would calculate the offset, so that's where it is in the block, would be, this is described with that. The line number, it would be in the cache, would be described by this, and then the tag would be this. And this is the address in main memory. And if you look at it, this main memory address would be 10, right? So 8 plus 2, so it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 would be right here. So 10 is the address in main memory. Corresponds to block 2, which, remember, the block is what's outside of the offset. And then the offset is 10, so it's item 2 in this block, 0, 1, 2. If I were putting it in the cache, I would put it in line 0 with a tag of 1. So as we saw, multiple addresses map to the same line number, and that can cause conflicts. A cache line can only hold one candidate block. So the two problems with this is that you may have lines that are just, the cache might not even be full because some line never matched. And it could, so this can cause performance hits. So fully associative doesn't have the performance hit of possibly not having a full cache, but then you had to do all those comparisons. This one, there are fewer comparisons, but there could be worse performance. So that, of course, there's always performance, there's always trade-offs. Okay, so the third option is somewhere between fully associative and direct map, and it's called set associative. And so we have sets of blocks that map to the same set of lines. So you can think of it as fully associative is one set, and we'll see how the set associative works. So two-way set associative means that there's two lines in a set. So each set has two cache lines in it. So if we have 14-bit addresses and we have a cache with 16 lines, 8 bytes per line, so a line has 8 bytes, so that means that tells us how big the offset is. So log 2 of 8 is 3. And then if we have 16 lines and 2 lines per set, that means we have 8 sets. So that means that the set number is also 3 bits because log 2 of 8 is 3. And the rest is the tag. So again, there's 3 fields. So now if we're saying, all right, I want to go to address, this address. So if we look at this as 14-bit binary, here's our binary address. This is the offset. And this is the set. So the set number is 1. We go to set 1 and see if either of the 2 lines in set 1 have this tag. If so, it's a hit. So here's an example with 32-bit addresses, 4 sets, 2 lines per set, and 4 bytes per line. So 4 bytes per line means the offset is 2 bits. Here's the set number is also 2 bits. So we go here and we find the set. Remember, there's 2 lines in each set. So if we're looking for set 1, there's 2 choices here. This one or this one. We check the tag. We see if the tag matches either one of these two. If so, it's a hit. This is some logic for checking the tags. So we want to check if either one of these two matches. If one of the two matches, it's a hit. And then if it's a hit, we send the data. So again, there's in this example, or the example on the previous slide, there was 2 spots. So when you map something to a set, there was 2 choices where it could be put. So if you want to put something new in the cache, it can go to any vacant line in the set. If all the lines in the set are full, you have to figure out how to replace something. And the most common choice, which we're going to look at shortly, is least recently used. The optimal replacement policy, you don't want to replace something that's actually been accessed, because you might want to access it again. But it's impossible. The absolute optimal, I don't know if it can't be implemented, but it's difficult to know which one, to keep record of what line was most recently implemented, most recently used. But we'll look at an approximation of least recently used coming up. So there's several policies, as we talked about earlier. Besides least recently used, there's first in, first out. So whichever's been in there longest is taken out, and it ignores when it was last used. So something, even if it was used a lot, if it was the one that's been in there the longest, it'll go. And then there's random. Just replace a line at random, which works and doesn't thrash. So thrashing is when you're repeatedly replacing something, taking it out, putting it back, taking it out, putting it back. That doesn't happen with random, but you could evict a line that will be needed soon or often. The best one is least recently used, but it is also the most difficult because you have to maintain an access history, and that is difficult. So we're going to look at an approximation. So we're going to look at a scheme used on the Pentium. It's just a good example. So it works with a 4-way associative cache. So in a 4-way associative, there are 4 choices. So when you map something to a line, there are 4 lines in that set. When you map it to a set, there are 4 lines it could go in. So what if you had a miss? You go get the data from memory, and you want to put that data in the cache, and you map it to the set number, and the set is full. So you have to figure out, what are you going to evict? And so you're going to use these 3 bits. So that's bit 2, bit 1, bit 0. So if you were describing the number, this would be B2, B1, B0. And this is going to be a number that is, a 3-bit number that's saved. And according to, it is changed according to which bit is most recently accessed. So if you read, write, or replace away, it's called an access. So every time, if you map something to a set, you go and you find that that was a hit and you read it, that's accessing it. So if you are going to, the bits start as 0, 0, and 0. If you get a hit and way 0, you're going to change bit 0 to 1, bit 1 to 1, and this one will stay. if the next time you access that set, you access way 2, you're going to change bit 2 to 1. Bit 1 will stay the way it was, and bit 0 will go to 0. Okay, so these numbers are constantly flipping based on what was most recently accessed. And so this 3-bit number is going to be your measure of what was least recently accessed. So I haven't accessed way 1 or way 3, so let's now do an access. So if we access now way 3, we're going to change bit 2 to 0, and bit 0 was already 0, so this will be way 3. So this is the value of our 3 bits right now. Now if you get a miss and you want to know what to replace, you look at the value of those 3 bits and use this table to decide what should be replaced. And if you remember, I did an access of everything but 1, and this is what the resulting 3 bits were. And if we look at here, way 1 would be the one to be replaced, and for this little example, that's correct because way 1 was never accessed, so it's definitely the least recently accessed one, so that was a good choice. So if you were to get a miss and need to bring something into the cache and it was full, and these were the value of those 3 bits, this is the one you'd replace, way 1. So that's when you have a set and you have 4 lines in it. You want to put something in there and they're all full. This is saying replace way 1. Okay, so now we're starting on a different subject. Cache is used to make memory appear to be faster. Virtual memory makes it appear to be larger. So this is saying virtual memory is saying my main memory isn't big enough. I need to pretend I have more that's out here on disk or whatever. So can I pretend I have bigger main memory? And I do that using what's called virtual memory. So let's go through a little vocabulary here. So logical memory makes our memory system bigger. So if this is our logical memory, the physical memory is a smaller part of it. Physical or main memory. And then we're going to break this up into things called frames. So this would be a frame in main memory, and pages. Logical memory is split into pages, so all of this would be in pages. Main memory is split into frames. And of course, frames and pages are the same size. So just like we had lines and blocks, just in another annoying, let's call the same thing 2 different things. So there are many more pages than frames. So pages are in the logical memory, frames are in physical memory, but having a lot of pages gives the illusion of a larger memory. And we use the program, when we have an address, we map it to a page, and then we use a page map table to map the page to a frame. And then if we find out the page we're looking for isn't in physical memory, that's what's called a page fault. Okay? So here's another simple example. Say we have a physical memory that's 4 pages or frames, 4 frames in our physical memory. Our virtual memory is going to be 8 frames. So we are having the illusion of having 8 frames of memory, but we can only put 4 of them in physical memory. So what we're going to do is when we look for an address, we have a virtual memory address where we say, I want page 0. And then you would go to what's called a page map table, go to page 0, and you'd find out, oh, that page actually is in physical memory. It's in frame 2. So we go to the physical memory and look for frame 2 to find that. So when we're using virtual memory, we're going to translate an address into 2 fields, a page number and an offset. We'd look in the page number into the page map table to find the frame number to look at, and then use the offset to find where in the frame we get that byte we're looking for. If the valid bit is 0, it means it's not in physical memory, so we have to go to the secondary memory to get it, and that is what's called a page fault. So our virtual address that we use is going to be bigger than our physical address. And so if we have 8K virtual addresses, so that'd be 2 to the 13 bits, or 13 bits, 2 to the 13 addresses, and we have a 4K physical address space, so that's 12 bits, or 2 to the 12th bytes in our memory. We would have, if we had a frame is 1K or kilobyte, that's 2 to the 10th bytes. So that means our offset, since our frame is 2 to the 10th, our offset is going to be 10 bits. Then the page number of our 13-bit address is going to be the top 3 bits. We get the page number, we go to the page frame table, then the physical address, because there's 4K of physical addresses, the frame number is going to be 2 bits. The virtual address has 13 bits because 8K is 2 to the 13th. The physical address has 12 bits, and each of them have 10 bits for the offset because the frame size is 2 to the 10th bytes. So if we have this 13-bit virtual address, the page field would be 101, which is 5. We go here and we find out that it is valid. It is in main physical memory, and it's at frame 1. So we replace, to get the physical address, we replace this 101 with this, put a 01 in here. Okay, so what kind of hit do we take when we're using virtual addresses? When we have to do 2 access, so first we go to the page map table to see if we can get a frame, and then we go get the resulting physical address. Okay, because translations take time, we can have a cache for the translation. So if we've done a translation, we can put that into the cache so that it's quicker to get it if we ask for that same memory again, and that's called the translation look-aside buffer. So here's a little chart. So if you have a virtual address and we want to know where the physical address is, we first look in the translation look-aside buffer. If it's a hit, we go to the physical address to get it. If it's a miss, we then look in the page table, and if it's in there, yay, whoopee, we go to get it. If it's a miss in the page table, we have a page fault and have to go to secondary memory. So this is a kind of combination of the virtual memory and the cache. So we're going to change the virtual memory address, get the physical address, and then look and see if it's in the cache. And so this is all the process you can use to determine, 1, is it in the TLB? 2, is it in the cache? And so all the options you can go through in that. And finally, here's an example system. We have our CPU, and on the chip we have our level 1 cache separate for instructions and data, and our TLB is within there. And then our level 2 cache is close. And then finally the main memory. And then encompassing all of that is the virtual memory. So we might have addresses for more stuff that's out of main memory. And virtual memory includes that too.